Let's consider another property of our conductors. Suppose we have an isolated conductor, and that conductor has a charge Q on it. Now remember, our conductor is an equipotential. That means every point in the material of the conductor is at the same potential. And let's choose phi of infinity to be 0. Then we can say that this equipotential value, phi, and now what we like to establish is the relationship between the charge that's carried on this conductor and the potential. They're related. And what we do, they're linearly proportional, so the charge is proportional to the potential with respect to infinity on that conductor. Now, the constant of proportionality is called the capacitance. And so what we have is that an isolated conductor has capacity to store charge. And C is the capacitance. And if we look at our SI units, that the typical capacitance in SI units is called the farad. And 1 farad is equal to a coulomb per volt. Now, recall that a volt is an energy per charge. Remember our definition of potential difference. So what we have here is a coulomb, and that's volt, remember, is joules per coulomb. I'll just look at it like that. And a joule, now we can put our, signify this, we'll use the C squared for coulombs, divided by a joule, which, remember, a joule, if you want to think about that, is just energy. It's a kilogram meter squared per second squared. And so we have this complicated relationship where we have coulomb squared, second squared, kilogram meter squared. And sometimes we denote this by an F for a farad. And that is a description of the capacitance of an isolated conductor with a charge Q. We'll now look at some examples.